It's my pleasure to introduce Jules Gardner. She's the electron microscopist guru at CNS for a decade. Yeah, for a decade. And she specialists in operation corrected TEM and electron energy loss spectroscopy. I'm getting my acronyms right. And so if you want to see individual atoms, you can go down and talk to her multiple days. And with that, I'll let you start.
Thank you, Arthur. So today I'm going to be talking about a technique called EELS. I think what was advertised was us to do a little bit of talk on aberration-corrected electron microscopy, but I decided I was just going to jump into it and just go straight for EELS because a year ago I gave a talk which had a lot more aberration-corrected stuff. So, and that recording's online, so you can always go find that too. But I'll start off with a few introductory slides just on electron microscopy in general, just so that we can all get up to speed. So throughout this seminar series, you're going to see a bunch of us standing up here and talking about different types of characterization. And that can be over different length scales. And this is what this plot here is trying to refer to. So Arthur's already given a talk on optical microscopy. And then we've got a bunch of other different techniques here. But about half of the staff here in the imaging group work on techniques called electron microscopy. And they cover a really broad range of length scales, as you can see from the light blue in the bottom there. So the most commonly used one is probably the SEM. And Tim will be giving a talk in a few weeks on scanning electron microscopy. So watch out for that. But what I'm going to talk about today is a technique which is transmission electron microscopy, or TEM. And that tends to be on the smaller length scale. So it's to the bottom left of this. Does this work? Great. So it's down to the bottom left of this diagram over here. So TEM, as I said, stands for transmission electron microscopy. It's slightly different to SEM in that it's higher beam energy, and that allows us to have less aberrations in the system, which is what allows us to push the resolution limits a little bit further. We use it both for material science, we use it for biological. We've got Nikki in the room, who is our biological science imaging expert, and I think she's going to be giving a talk on that later in this series. So the idea is that we have a very thin sample, which is different to an SEM where you've got a bulk sample. In TEM, the transmission means you're going to have a thin sample to get the electron beam through it. And then you're going to be using a variety of different imaging techniques and analysis techniques to try to learn as much as you can about your sample. So there are two main types of transmission electron microscopy. There's standard TEM, and that's what we start all our new users off on. In TEM, which is the diagram on the left here, you have a broad beam of electrons which are hitting your sample and passing through it. And that's interfering with the sample and generates an image. And we can project that image plane onto the camera at the bottom of the microscope. So the electron beam starts at the gun here, works its way through, here's your sample, and then ends up on the CCD here as an image. This is nice. It's less beam sensitive when we use the TEM in general. And we're able to get really quickly some images out of a system relative to TEM anyway. Then we have on the right there, scanning transmission electron microscopy. And that's what we're going to be talking about a lot today. And it's a lot of what I do myself in the lab. And it's kind of a marriage between TEM and SEM. So it takes kind of components of both. So in an SEM, if you guys are familiar with SEM, what you're going to do is you're going to have the beam in one spot. You focus the beam to one spot. You measure the detector output. Then you move it to the next spot, measure the detector output, and build up this raster pattern so that you can gradually build up your image that way. That's what we're going to do in a STEM as well. So we're going to take the TEM probe. We're going to make it as tiny as we can. And we're going to focus it on one spot, then measure our signal, then move over to the next spot, and then move over to the next spot. And because we're at these higher energies and we've got more complicated lens designs, we're able to beat the resolution by an order of magnitude at least on a standard SEM. So TEM is a little bit easier to use and it's a little bit more forgiving, but scanning TEM or STEM is really helpful, especially if we're wanting to do analytical work, because we're able to get information from different positions within the sample. And whereas in TEM, you would just get one agglomerate spectrum from that. So we have 6 TEMs at CNS. I just want to introduce those guys to you. So we have the Joel 2100 and the Joel F200. So the 2100 is over in Cambridge. The F200 is basically its newer replacement, which is in this building in the SEC. Then those two are more materials science-based tools. Then we have the Hitachi 7800, that's Nikki's tool, and then the Therma Arctica, which Nikki also works on along with Stefan. So the Arctica, it's got a cold-sounding name, and therefore it is our cryo TM. And you've got the big liquid nitrogen drawer next to it too there. So that's going to be used for single particle analysis, and that's actually something that's just really coming back online after a little bit of downtime. So if you're interested in that, see Nikki, see Stefan. If you're interested in straight up biological imaging, see Nikki. And then on the right-hand side, we've got our two aberration corrected microscopes. So these are going back to the materials side again. We've got the Joel ARM, which is what I spend most of my time on. And then we've got the Hitachi Megascope. I believe David is giving a talk in a few weeks about everything that this tool is going to be able to do. But for our purposes today, on talking about eels, it's these two end microscopes that have the EELS systems in our center. So I've talked about the different hardware we have for STEM and TEM. Well, what do the images actually look like? Well, one of our favorite things to image in the electron microscopes is gold nanoparticles. Whenever you come for a training, the first thing we're going to do is get you to image some gold nanoparticles. So I thought I'd use this as an example. So on the left, we've got a TEM image. You can see it's a gold nanoparticles in a very thin carbon grid. So you can see this mottledy appearance of the amorphous carbon. And if you look really closely, you can see some lattice here of the gold nanoparticle due to its crystallographic axis. Then if we take that same sample and we put it in STEM mode in the microscope, we get the two images on the right-hand side. We can look at the straight electrons, which have been just straight through the sample. That's the bright field image. And that's going to look very similar to our TEM image, but you'll see we get a little bit better contrast in the system. And then what we can also do is we can look at elastically scattered electrons at high angle, and that's going to give us an image here which looks like it's inverted. And that's because gold is a stronger scatterer than carbon, and so we're going to get more signal when we're on the gold nanoparticle than when we're on the gold nanoparticle. Conversely for that, when we got a bright field image, when we're on the particle, we're going to get less beam transmitted straight through the sample than we are in a thin sample like carbon. So in STEM mode, what we like to do is we like to try to image individual atoms. So here is an image with individual atoms. This happens to be a silicon sample, which is another standard sample that we like to use. What this is showing you is on the left-hand side, we've got our Joel F200 microscope. And on the right-hand side, we got our ARM. So the ARM has an aberration corrector. And as you can see, hopefully, this image is a little bit sharper than this image on the left-hand side. So the reason for that is these microscopes, as you saw from the pictures, are a little bit taller than the other standard microscopes. And that's because they got a whole new lens system whose job is to correct for any aberrations in the system. So what we do is we run a program on the computer which calculates the aberrations in the lenses. And then it says, okay, I'm going to reverse that, and uses that to try to correct for the aberrations. So this has been happening for the last 20 years or so now that we've been using these aberration corrected instruments. On the right-hand side, we can see the resolution from light microscopes, how electron microscopy really helped us to see finer and finer details. And then at the top here is the birth of aberration corrected, and it's really helped us to push further into the resolution of these systems. So we have a variety of different signals we can collect in TEM and SEM. It's not just about getting pretty pictures. We can also collect other signals. So in an SEM, for example, you're going to be using secondary electrons, backscattered electrons, and those each have different information. For example, backscattered electrons, you're going to be able to get more atomic number contrast than you will from standard secondary electrons. We can have X-rays coming off the sample. That's going to be a technique called EDS, which I guess Tim will be talking about a little bit in his lecture that's coming up. So that's a way of fingerprinting the materials, the chemical elements which are present in your material from these characteristic X-rays that come off. We can also look at light, so cathodoluminescence. We actually used to have a holder here at CNS which could do cathodoluminescence in the TM. We don't have that anymore. Then down the bottom here, because it's a thin sample, we can get elastically scattered electrons and inelastically scattered electrons off of the system. And it's these inelastically scattered electrons which we're going to be using for EELS. So, as mentioned, elastic and inelastic scattering. I want to go into that in a little bit more detail. So on the left here, we have an example of what elastic scattering would be. So the idea here is the electron comes in and doesn't lose any energy as it interacts with the material. However, sometimes what happens is the electron comes in and it can knock out core shell electrons. It can excite them to other levels. And that's going to cause what we call an inelastic scattering. That's because to excite these electrons into other levels or into conduction band is going to mean that we're going to need to put energy into the system. You've got to knock them out, right? You've got a hammer, you've got to knock it out. And that energy, it has to come from somewhere. And where that's going to come from is the incoming electron beam. So therefore, electron beam comes in at a certain energy, causes one of these interactions and comes out at a slightly lower energy. And that's the whole idea of EELS is we're going to collect the electrons that come through and look at their energies. And from that, figure out what the energy of difference is from the electron that's come through it to what came in. And then we can figure out that delta energy. And that tells us about the different transitions that are in material. So we can look at an energy level diagram like we have here. This is for just two elements, nickel and oxygen. We have our different shells that we talked about before. So 2s, 2p, 1s, 3s, 3p, etc. And there are allowed transitions between these different levels. So what we can have is we can have electrons coming up here. We can have electrons coming up to the conduction band. We can have electrons which are just below the Fermi level and the valence band, also coming up into the conduction band. So there's a series of different energy level, different transitions, and they all have different energy because energy is plotted on the y-axis here. So what that gives us is a plot, which like the cartoon shown on the right-hand side. Here we have energy loss. So we take, say we start off with 200 kilovolt electrons, we measure the energy of the electron that comes through it, and we find that delta. We plot that along this x-axis, and then we just plot counts on the y-axis. And it gives us something that looks like this. So we've got the zero loss peak here. These are the electrons which haven't lost any energy. They've just gone straight through the material and not interacted with it. That's actually really helpful because we know that, therefore, that's at zero, so it allows us to calibrate our x-axis. We then have a bunch of low energy electron transitions, which are down here. And then going down lower and lower intensity to make it clearer, what we've done is we've magnified at this point the y-axis tenfold, and then we see these weird kind of bumpy things like this here. And these have a lot of information on them. They're called ionization edges, and we're going to go into some more detail about what these are shortly. So the types of information you can get are, you can get sample thickness, you can look at where the band gap energy is, you can look at plasmons, you can look at the elemental composition, you can look at what the oxidation state of your material is, you can look at things like coordination number around the material. So there's an awful lot of rich information, and I'm going to give examples of all of these guys. Yes. Before that, we are going to just look and see how we achieve that. So TM's big tool things, we showed pictures of before. Right at the bottom, there's a viewing screen. If you've ever been and seen a TM and looked at it, this goes up green when we're using it. If we remove that, so flip that out the way, and we bolt on a spectrometer, what we can do is we can focus the beam into a biprism, sorry, not a biprism, a drift tube. And what the idea is here is that electrons of different energy are going to be bent, there we go, bent differently, depending on the incoming energy in this rounded drift tube here. So that's going to separate them out in space. So some of higher energy are going to be bent less than ones of lower energy. So we're going to have a spectrum here. And then what we can do is we can project that onto a CCD, and it gives us something that looks like this, which is like the cartoon I just showed, where this is your zero loss, and then here you have some more information coming along. The CCD looks something like this. So this can be just the same as a standard TM imaging CCD. So the electrons come in, they go through a scintillator, and then they convert it to light, and then we can measure the signal intensity there on a pixelated detector. These days as well, we're getting even fancier or more expensive, and we're using, instead of this CCD type arrangement, we can use direct electron cameras. These don't have all of this conversion here, so they're a lot more sensitive, which is great. They're also a lot faster, so we can collect our data a lot faster. But the downside is A, they're way more expensive, and B, they're also a lot more sensitive to damage. So we have to be a little bit more careful when we're using that kind of system. Okay, so going back to the mechanics of what's happening between the electron beam and the sample. We've got a sample of a finite thickness as shown here. Electron beam comes in and it can interact. It can interact here, 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 and here. The number of interactions as it passes through the sample is going to depend on a few factors. One of those is going to be what the atomic number or the density of the sample is, right? You can imagine if you're a ping pong ball and you're trying to get through a room, if you've got lots of big targets, you're going to be bashing into them more than if there are lots of small targets. As well as that, it depends on how fast you're moving through the room. If you're moving fast, you can kind of just take a straight shot. If you're moving kind of slower, you're going to be interacting a little bit more. So that's what these plots here are showing that we do have a fairly contained distribution of what the distance here, which is we call our mean free path, versus the atomic number or effective atomic number in this case, because we might have a compound of some description. It's not just a pure element, or the density. And then you can also see that you've got a higher mean free path. You can go further for a higher energy than you can for lower energy. What that means is we can start to get more interactions if we've got a longer mean free path, shorter mean free path actually. And if you've got more interactions, you're going to generate more kind of features in your spectra. In particular, what we see are these plasmon resonances where you've got your zero loss peak here, and then you've got this separate plasmon resonances over here. And if you're interacting more with your sample, you're going to get more of these transitions occurring. And so you're going to get this kind of plural scattering, what we call plural scattering. We got a bump here, a bump here, a bump here, and a bump here. So this depends on the thickness of the sample for a given material. So if you've got a thinner sample, say it's only 0.15 mean free paths, you're going to have the solid blue curve there. And then as you go up in thickness, and you keep increasing the thickness, you're going to have more interactions. And so you're going to end up with this more bumpy material, bumpy EELS spectrum here. We can use that information to try to figure out what the thickness is, right? So if we had like no material at all, we would just end up with the zero loss peak. So we would have I0 here, and then we would have just a complete flat line here. However, our samples have an actual thickness to them. And depending on the thickness, we're going to have a different ratio of these bumps here to this peak here. So what we can do is we can integrate under all of the spectrum, and then we can integrate just under this peak here, and we can take the ratio of it, in fact, the log of the ratio of it. And then if we know our material, say we're using silicon, we can look up the mean free path of that, and then we can calculate the thickness, which is T here. So it's kind of a really nice way to measure that. As well as just getting a measurement from a spectrum, we can also measure different on a line scan or a map. So we can generate a lot of information about the thickness of our sample that way. So we mentioned plasmon peaks. So plasmons are a very interesting branch of physics all on their own. So we can be mapping out these plasmon peaks to see what energies are locally, the plasmons are present in the sample. So we'll see different shifts of different plasmon modes depending on what is present in the sample. We've got an example of that coming up here. So these are some silver nanoparticles. They're about 50 nanometers. This is 30 nanometer scale bar here. And the top here is some experimental EELS data, and the bottom is the theoretical. So you can see it matches pretty nicely. What we've done is we've sat at each point and we've measured the EELS spectrum, looking at the low loss region because we're interested in the plasmons. And then we've taken the spectra and we've fitted it to peaks around 1.8, 2.7, and 3.2 eV. And then we're able to see the localization of these different plasmon modes. So we can see this one here is very localized at the apexes. This one's here is on the sides. And then this one here is slightly more in the middle here. So that's kind of cool. Another thing we can do is we can measure the band gap of different materials. So the idea here is that between the Fermi level and the highest occupied level, there's no states there for the electrons to go into. So what we're going to see is we shouldn't see any EELS signal in that region. But then once we start to overcome the band gap, we can start to see these transitions occur. So that's what this diagram is on the right. This is silicon dioxide. And the idea here is that we've got pretty much zero down here, and then we see this peak here. So this allows us to measure the band gap of 8.9 eV. This plot is just showing you different thicknesses because you can measure different thicknesses of material. So one thing we really commonly do when we're doing EELS, probably the most common thing, is this thing called core loss electron spectroscopy. So we're no longer looking at the low loss, we're now looking further out on the energy scale. And what we're seeing here are these transitions I mentioned before when we had the Bohr model, and I showed the inelastic electron scattering. We've got our levels, our different shells, our K shell, L shell, M shell, N shell, and O shell along the bottom here. And then depending on where the electron originated, we're going to give it a different label. We're going to call it a K shell, an L shell, an M shell, and then up we go. And these correspond to coming from the 1s, the 2s, the 3s, the 4s, the 5s. K shell is the most simple. You've just got the two levels there. So you're going to have a much more straightforward EELS signature. So what happens here, this is the example of the K shell. You've got your background coming down here, then you've got a sharp increase when you get to that energy, and then it follows the background again. So it's a nice, we'll call it a sawtooth of shape, line shape for that core loss spectra. Others are more complicated because you've got more levels here from which the electrons can come. And so therefore that corresponds to more complicated line shapes of the edges. So from just at the edge shape, we can actually even identify whether it's coming from a K shape or an L shape straight away. Another thing we might want to do is figure out how much of our material is, not just what it is. So once we're identified what our peaks are, we can come along and we can integrate under the peaks. So because this is our background, anything above that is coming from transitions which are coming from that particular elemental transition. So we can integrate under this and we can get an intensity here. And then we've got another element over here. So we can integrate the same width here so that we've got our counts here. Different elements have different probabilities of generating these transitions. We call those cross sections. So something heavier is going to scatter more strongly. So this cross section is going to be different to something that's lighter. So we can look those up. These are well-known values. And so once we plug in those values and we plug in our measured intensities, we can get the relative intensity of our different elements. And we don't just have to do that for one spectrum. As I said earlier, in STEM mode, we're able to scan. So we stop the beam, make the measurement, stop the beam, make the measurement. And we can do that for all different types of signals simultaneously. So we could be collecting EDS and we can collecting EELS at the same time, as well as collecting our standard HADAF image as well. So we've got a very rich data set. What the data set looks like is portrayed in the cartoon on the right there. So you've got your 2D map, but within each of those, you've got a whole spectrum which goes along here. So it's a really 4D data set that you've got going on. Sorry, 3D data set that you've got going on. So we'll take an image of a device, for example, what's shown here, and we can pull out different spectra. So as you can see, all of these peaks change depending on what area, which is highlighted in red, of the sample of the image that we're looking at. So that helps us to then ID like where this energy level is, where here it is. We can tell if they're different elements, and we've got different things going on over here too. And then if we push that to the resolution limits of the STEM, we can start to ID different individual atoms even. So this is strontium titanate. This is another one of my favorite samples to look at in the STEM. This is the HADAF image where you can see these slightly brighter and darker elements. This corresponds to strontium is the heaviest, and then you've got the titanium, which is the green here. I do realize that I've miscolor coordinated everything here. So in this diagram, strontium is red, and down here it's blue, but we'll just gloss over that for right now. The main point here is that we can very clearly see that where we've got titanium, we don't have anything for the strontium, and then when we've got the strontium, we don't have anything for the titanium. So we can see this alternating layer, and then we can overlay it in the top up here. For the oxygen, we can see the fourfold symmetry of the oxygen coordination around this too. So we've learned that we can do elemental composition. That's great, but we can also dive even further to get more information out of this stuff. And that's from looking at the structure of these edges. I said that one can be a sawtooth, one can be a bit rounder. But if we compare individual line shapes, we're able to get even more information out. So we have this thing called near edge fine structure, which, as the name suggests, is near the edge. And then as we go further out, we get these other perhaps weaker oscillations, which are going to tell us more about the local environment or the coordination number of the atom. So unfortunately, it's not quite that simple because we've got our low loss spectra to contend with too. So everything in the low loss is going to be superimposed on what we see on the core loss. So say we've got this cool edge here, which is the theoretical edge of this is like a transition metal spectrum. What happens in reality is this is our plasmon peaks that I explained earlier, also with the zero loss peak. So then we end up with this very blurred kind of spectrum in the end. So we spend a lot of time trying to figure out how to deconvolve these. Unfortunately, modern software allows us to do that as long as we collect the low loss and the high loss at the same time. So we go back to this diagram that I showed earlier where we've got the unoccupied density of states. So we're able to see all these different transitions and they correspond to different energies. And what that means is as we go from the core up into the conduction band, we're able to then just nicely map out the unoccupied density of states here. So that's kind of cool. And this is what it would look like on the actual spectrum. So we come up here and we subtract off the background and we'll be able to get this nice density of states map here. In reality, what does this look like? Well, here's an example of carbon. Everyone's familiar with different types of carbon. So we see these very different line shapes. Here's the core loss and here's the low loss. So these are the plasmons in the energy range of up to 50 eV. We can see some changes in the plasmon resonances as we go up between amorphous graphite and diamond. But if we go to the core loss, which is nearer 284 eV, we're able to see some more dramatic changes here. So this is why we tend to use core loss spectroscopy for identifying the different complexes of the material that we have, is because it shows this up a little bit nicer. So you might be saying, well, I've already heard of a technique that can do that, X-ray spectroscopy, and you're absolutely right. So this is a comparison between what we can get on eels on the left-hand side and what we can get through X-ray absorption spectroscopy of various different manganese oxides. Hopefully I can convince you that not only do the eels data look different for the different manganese oxidation states, this one's a lot sharper, this one's a lot broader, for example, but they very neatly match the X-ray absorption spectroscopy. And that's because we're probing exactly the same thing here. We're probing the unoccupied density of states, and that's the same for the material. Advantage of eels over X-ray spectroscopy, though, is you've got the spatial resolution tied into it, whereas X-ray absorption spectroscopy, you've got a much bigger spot, so you don't get as high a spatial resolution. So here's an example of mapping out oxygen and titanium across a boundary here of a fabricated device. So we're going from this barium complex to this magnesium complex. And what we're able to see is as we're down in the barium, we're able to see this oxygen edge here, and then it changes to here. And then between this guy and this guy, we're seeing quite a big change. And at the same point, if we look at our titanium edge, we're able to see this line shape, which stays pretty similar, and then all of a sudden it changes. So what that's telling us is the oxidation state of the titanium is changing somewhere between these 2 points. So even on the atomic level, we can measure the oxidation state, which is kind of cool. The way we're doing that often is to use, well, most commonly will be for transition metals. So the different transition metals have a different line shape, and this is due to spin-Hilbert coupling. So we get this, what we call a pair of white lines, which are these characteristic L2 and L3 peaks here. And then as we go along the periodic table, we see their ratios changing and their separation changes. But one cool thing about that is that it's not just that as you go along the periodic table, they change. As you change the oxidation state, you're also changing the ratio of these two peaks. So from just plotting the ratio of the L2 to L3 peaks, we're able to get a lot more information about what the oxidation state is locally. And that's how that example a couple of slides was done. They were just changing the ratio of those two peaks and able to compare that to the literature values to figure out whether they had titanium 3+ or titanium 4+. So as well as that's the near edge spectroscopy, we can go further out and do XELFs. This is analogous to XAFs in X-ray spectroscopy. So what we do here is we get rid of this big peak here and we just start here and we fit the background and we subtract off. So this is just carbons, graphitic carbon. And what they're doing is they got this peak here. And similar to XAFs, you're going to run that through some software and it's going to be able to figure out your nearest neighbor distances. So here you've got 1.08, 1.84. So you're able to figure out all the different coordination numbers or the radial distribution function of your material. So that's cool. And then lastly, I want to talk a little bit about a related technique to EELS, which is called FTEM. We have this on our Hitachi Megascope. So in EELS, we had an image earlier about the spectrometer. This is the bottom of the TEM. In we come, and then we've got a spectrum here, and then we project that onto the CCD. And so then we've got this thing here, which then if we measure a line along here and measure intensity, we get our EELS spectrum. However, in the TM, we like to play games. And one of the things we like to do is to change what projection we're projecting onto a CCD. So sometimes we'll project a diffraction pattern, sometimes we'll project an image. Analogous to that, the EELS spectrometer can either project the spectrum onto a CCD or it can project the image. So you're like, well, why would I do that? I could just put a CCD there. That's kind of silly. But one of the cool things is at this point here, we've still got the spectrum because that's what's come out of the drift tube. So then we can apply a mask onto that, and then we can just use electrons of a certain energy to form the image that we're using. So similarly to what we had before, we've got the electrons hitting the sample, coming in, using the slit to decide what energy range, and then we get an image here. And then what we can do is we can keep moving the slit in energy space across the sample, sorry, across the spectrum. And then we build up all the stack of images. And then if we slice down here, then we get back our EELS spectra. So it's kind of the same thing, but in reverse. So why would we do that? Well, here's a couple of examples. So on the left here, we've got a diffraction technique called seabed. I haven't talked much about that, but what it does is it gives us a lot of cool information about the thickness of the sample and any other interactions which are going on in the sample in terms of its crystal structure. And here is just a regular seabed pattern of silicon, I believe. And then on the right here, yeah, silicon 110. And then on the right here, if we just energy filter it, so we've just got the zero loss peak, we can get rid of a lot of this blurring, which is coming from these inelastically scattered electrons, and it makes it a lot more easy to interpret. Another example is we can take a regular image, a regular bright field image of a device here that someone's made. And then if we're looking to see some plasmonics, for example, we can put a slit to an energy which corresponds to wherever those plasmonic resonances are, say 50 eV, and then we're able to see locally where those plasmon modes are lying. So that's kind of cool. As well as this, we can do chemical imaging. So we can sit at the different core loss edges. So on the left here, we've got our bright field image of some steel, and you can't see an awful lot of information about where the different elements are coming from. But if you want to sit your filter on different edges, for example, the moly, the chromium, and the vanadium, you can get different color maps and you can see where these are. You could also do this in STEM EELS for sure. but the dosage is lower in FTEM. Stainless steel. Steel would be fine, but if you've got a more beam sensitive sample, you might want to do FTEM for this. So you're not destroying your sample and you can still pull this information. So throughout this talk, I've been pulling resources from these two really cool places. So if you're interested in learning more about eels, I would definitely recommend Egerton's book. It's a kind of the Bible of eels, so definitely check that out. It's also available for free on download, which is nice. Another good electronic research resource is eels.info from Gatan. They have this thing called an eels atlas. If you click on the tab up here, it brings you up to the periodic table and it gives you example spectra of different compositions. So if, for example, you're looking to do core loss spectroscopy and you want to see what the oxidation state of Ti2 plus versus Ti3 plus, it actually gives you spectra that you can download and then you can directly compare it to your measured spectra. Okay, so in summary, eels is cool. You can do lots of cool things with eels. There's a list of it there. And if you are interested in doing some eels at our center, you can either come to the Joel Arm and you can come see me, or you can go see David on the Megascope. All right, thank you very much.